Hello, good morning. Am I audible?
Yes, sir.
Okay. Good morning and welcome to lecture on advanced power electronics. Yesterday we discussed zero current switching, a resonant switch converter, or a ZCS resonant converter, and we have shown it here. We can use here. We have earlier to that we discussed the one of the method of commutation of thyristor, and that is we can call as a Morgan circuit, or we can call as a class B commutation. So here in case of thyristors, we want to require a commutation circuit to turn it off. Job of commutation circuit is to make the current through the device zero and then apply the reverse bias, and this is done by the this circuit. But when we are going for a fully controlled switch here, and in that case we can use a resonant circuit across the switch. So here we have seen that we have connected a inductance in series with the switch and connect a capacitor parallel with series combination of switch and the LR. And yesterday we discussed the operation of this. Our current is, our switch is turn on at zero current and turn off at the zero current. And we have also seen it here. So particularly in both cases, turn on and turn off, we have seen that here, particularly at T0, our switch is turned on, and because our current is zero, earlier switch is off, so turn on at zero current. Similarly, because of the LC tank circuit, our current will reverse, uh, try to become maximum. So current, it is a LC tank, earlier our capacitor is charged. When you turn on the switch, this capacitor will try to discharge and charge in the opposite direction. Okay, and whenever this, it will try to reverse the current, but here switch is unidirectional, so a particularly current will become zero. At T2 our switch will turn off. So this circuit particularly used for zero current switching, and our losses will be eliminated with this. Here one important thing is that this is on time. Whatever you can see that T0 to T2, that will be on time of the switch, and this on time is fixed based on the values of LR and CR. Based on the LR and CR, this T0 to T2 will on time will fixed. So here in this case ZCS, particularly this buck converter, our T on is fixed, and we can vary the T off. So here we can say that we can vary the frequency to control the output voltage. And as our output voltage increases, as frequencies increases, because as frequency increases, our off time will reduce, on time will be remaining fixed. So here in this case, we control the output voltage by controlling the frequency. As frequency increases, output voltage will increase. So this is we have discussed last time, and the summary of this. So LC resonant current passes to the switch, and switch is turn on and turn off at zero current. Output voltage is controlled by controlling the switching frequency, and switching frequency is less than the resonant frequency. That is required so that our switch will be turn on and turn off at a zero current. So this is one topology we are having, a resonant switch. So our L and C circuit across the switch, so that switch will be turn on at zero current and turn off at zero current. But here if you see the voltage across the switch VC, that VC will be we are having a higher value. uh, in this case it will be a possible, sorry, here ID, that is our current through the switch, will be higher. Voltage will be, in case of zero current switching, our current through the switch will be a higher. It may be almost a rated current I0 plus VD by Z0. So in case of ZCS, a current through the switch will be a higher. That is a drawback of this scheme. The switch has to carry a more current in case of a ZCS. So any question on ZCS? Turn on and turn off is at zero current. So our on time of the particular converter, buck converter, on time is fixed. By varying frequency, we can vary the off time. And by increasing the frequency, you can reduce the off time, and so that our duty ratio will be increased and we control the increase the output voltage. So as frequency increases, our output voltage will be increases. So any question on ZCS? Turn on and turn off both at zero current, and so the switching losses will be very less in this case. Any question? Am I audible?
Yes, sir. No question.
Sir.
Now let us go for next topology, that is zero voltage switching. We can call as ZVS, zero voltage switching. Again here our turn on and turn off is at zero voltage. So here we are having, so if you see it here, again this is a buck converter, a DC to DC buck converter we represented here. And here if you see it, our VD is the input voltage. This is a switch, a fully controlled switch, maybe IGBT or MOSFET we can use it. And through the series switch we are having a resonating inductor LR. Across the switch we are having a capacitance, resonating capacitance CR. So LR and CR and the DR, these are the parts of the resonant circuit. LR, CR and DR, they will be a part of resonant circuit. And here if you see it here, this LF and CF, they are the filter values, filter inductance and filter capacitance. And this is our load resistance, a diode we are having. Okay, we require this. And now, so this will be buck converter, a DC to DC buck converter. Output voltage is controlled by, again, indirectly we are controlling the duty ratio here. So by controlling duty ratio, we can control the output voltage. But here in case of duty ratio, our one of the time is fixed. In case of ZCS, we have seen that our turn on time is fixed. Duration for which switch remains on, that is fixed. But here also we can see here duration for which switch to be turned off, that will remain fixed. Okay, so that will be a, we can call as a the dual of whatever we are having as the ZCS. Now let us how the circuit operates. We can discuss this. Okay, so we have discussed the components. Now let us assume that a steady state condition we are considering. Let us assume that switch is closed. Let us assume that switch is on. We are in the steady current. So we are considering this period where this period before T0. Okay, before T0, our switch is on, continuously on. Or we can say it here, particularly this case after T3. a 4 region. If you see the fourth region where we have shown it here, our current is a constant. So this will be a whatever we can call as a here. And but okay, so we shown here before T0 our switch is on, so it is continuously on. So what will happen to the voltage across CR? When the switch is closed, capacitor is shorted, is it right? When the switch is closed, capacitor is shorted. So under steady state condition, when the switch is on, voltage across capacitor is zero. Voltage across capacitor is zero. Current will pass through this LF, this LR, LF, and then. So here we can say that our load we can represent as also current source. No problem. If the CF is very small, we can say that our this LF, CF, and R that we can represent as a current source. So equivalently, these three components, LF, CF, and R, that combinedly load, whatever this load, we can call it as a I0. So this is our current source. If you see it here, equivalent circuit, this will be a current source. Here we are not shown in the equivalent circuit diode. This is the diode. We are not shown it because it is not taking part. When the switch is on, we are shown that diode is this D is a reverse bias, so it will be turned off. Normal is whenever switch is on, diode is off. And so here when the switch is on, our diode is off, so we are not shown in the circuit diode. We are not shown it here. This LF, CF, and R that we represented as a current source. Our DR and CR we are not shown because voltage across the CR is zero. DR is not conducting, so we have removed these components. And equivalent circuit when the switch is on will be represented by this circuit. Okay, equivalent circuit we have shown it here. So switch is on, a current will pass through the LF, LR, LF to the load, and it returns back. So this will be a path, whatever we have shown it here. When the switch is on, we have marked the path of current. It will start from red, it is marked with a red. Okay, so from positive of the DC supply to the switch, through LR, through LF, to the load resistance, and it will come back. This is the path of the current. So this is the operation we have shown it here when the switch is on under a steady state. Let us consider at T0 we turn off the switch. We want to turn off the switch. When we turn off the switch, we have seen that we are having a capacitor across the switch. And during turn off, we have seen that voltage across capacitor is zero. During when the switch is on earlier, so voltage across capacitor was zero. When you try to open it, the voltage across capacitor is zero. So here at T0, if you see that a voltage across the switch VC is nothing but the voltage across the switch. So our voltage across the switch is zero. So at T0, we turn off the device, and this turn off is at zero voltage. Is it right? So at T0, if you see it here, at T0, we initiate given the signal for turning off the switch, and when the switch is turned off, we are having path of current. Now here we are having the case that is our capacitor voltage VC and the supply voltage VD, and let us assume that our capacitor voltage is less. Then what is the path? Here we are considering up to at instant T1, capacitor voltage and supply voltage will become equal. We are considering the period T0 to T1. We are considering the period T0 to T1, where T0 to T1, where our capacitor voltage VC is less than VD. And how is the path? Our switch is off, load current will be there. So path of current will be from the VD. It will go through the capacitor CR. Then we are having LR, LF, load, and it will go on this. So this will be path of current during the T0 to T1. During T0 to T1. Our switch is turned off at T0. But now current will be flowing like this, and because of that a capacitor will start charging. Capacitor will start charging. So is it clear? We have considered the instant t0 where our switch is turned off, and whenever switch is turning off, a capacitor is uncharged capacitor is coming across the switch, and because of that we can call this will be a zero voltage or turn off. We can call it as a zero voltage or turn off. So our device we are turning off it here, and we have seen that initially voltage across capacitor is zero, and we have shown the path, and capacitor will start charging, and this will be up to t1. At instant t1 what happens, our capacitor voltage will be equal to a vd. But now after that, because of the energy stored in the inductor, and now here you show it here, this will be our here whenever the switch offs, and after this particularly the t1, after this t1 what happens, because energy stored in inductor, it will be free will through this. So during t1 to t1 dash or t1 star, let us go for the period t1 to t1 star. At t1 what happens, now the capacitor current we have seen that, okay, this was the earlier path of the capacitor, now it will flowing through this. When after t1 what is happening, after t1 our diode will be on because of the lf, because of this energy stored in the LF. It is a conduction continuous current. So I0 is a constant and ripple free. We assumed this I0 is constant and ripple free. And whenever this current tries to decrease, okay, then definitely the diode will turn on, and whatever energy in the inductor will be dissipated this. So our diode is on. So here this is I0 and diode is on. And as diode is on, here we are having now a LC tank circuit. Now it is a LC tank circuit. And whenever we have shown that because of the inductor energy, we have seen that a red will be a increasing current. A red will be our increasing current up to this. Okay. So red we have seen that that will be our increasing current. And whenever current, red current becomes zero, it will try to increase it. It will be sorry, this red current is the positive current, and this current will be goes on decreasing. Why it is goes on decreasing? Because the capacitor voltage goes on increasing. And whenever this red current, that is positive current, it will become zero, it will become zero. This will represent up to t1 dash, you can call it. So this particular t1 to t1 dash, our red waveform we have shown it here, and that current will be goes on decreasing, and at one instant t1 dash, here we have shown that our current will become zero. And whenever current becomes zero, it is LC tank circuit. Current will try to reverse its direction, and now the current will try to reverse its direction, and that reverse direction of current is shown with a blue current direction, a blue current direction. And now we have shown it here, our current will be reversed because of the LC tank circuit, and here this negative current, okay, will flow through the diode, will flow through the diode. And now because of that, okay, this negative current will flow through the diode, and as a diode is there, okay, here we have shown it here, this case, and this is the equivalent circuit. And now we have shown it here again, because of this at t2 dash, at t2 we have seen that our voltage across, because of this sorry, so we can correct it here. Whenever positive current, let us consider again once again, positive current will goes on decreasing, it becomes zero, okay. And once current becomes zero, our LC tank circuit is there, okay, and tank circuit is because of that our current will flow in reverse direction. Okay, capacitor will be in series here. Okay, and because of the tank circuit, our capacitor voltage will be goes on decreasing. When current becomes zero, capacitor voltage will be maximum, and when current goes to the negative opposite direction, whatever this current will flow through this CR, and because of that, capacitor voltage will come to a zero at T2. So during this period, particularly when the switch is off, that duration will be T0 to T2. Duration for which our switch off instant, we can say it will be a T0 to T2. And during this period, our switch is off, and this switch off depends upon the values of LR and the CR, values of LR and CR. So here we can say the off time of the switch, here off time of the switch, how much duration switch should made off, that depends upon the values of LR and CR. And for a particular values of LR and CR, our off time is fixed, that duration T0 to T2, that period is fixed. Now here, so we have seen that our capacitor voltage, so we have seen it here, particularly this case, whatever our current diode is not conducting, I have made a mistake earlier here. So in this period from T0 to T2, we are discussing our switch is open. Initially current will flow whatever a red path, so that our that is a positive current is represented as a red path. So increasing of this current will shown it here. And when our current reverses its direction, and that current will be reverses whatever we shown with a blue color, and that same current is again passing through the capacitor, not the diode. Okay, that will be a reverse current, we have shown it here. And because of that, so our voltage again comes to a zero. And now again our it is not increasing another direction because of the diode. Okay, because of the diode, so voltage will remain maximum and then goes to the zero, but polarity will not be reversed here. So whatever the voltage across the capacitor here, that polarity will remain the same, positive only, but its magnitude will go to a higher value with a red current, and the magnitude will goes on decreasing, become zero with the blue current waveform. But direction of voltage across the capacitor is never reverse, because when your capacitor voltage reverses, immediately diode will start conducting. So diode is connected, so only capacitor voltage we are having is only marked polarity will be obtained. Its magnitude will become increasing when we are having a red current is flowing, and its magnitude goes on decreasing when our blue current is flowing in the circuit. So this will be operation, particularly we have discussed when the switch is up, and when voltage becomes zero. Okay, when voltage becomes zero at T2, let us assume that this is the instant when voltage becomes zero. When voltage across the capacitor becomes zero, we turn on the switch. We turn on the switch, and as we have shown it here, as we turn on the switch, what will happen? We have shown it here. The switch will be a turn on at zero voltage. Switch will be turned on at a zero voltage. But now our current flowing will be of the negative direction. So initially, though it is a voltage becomes zero, when voltage at T2 voltage becomes zero, we can turn on the switch. We can turn on the switch at T2. But switch will take a current. Earlier to that, our current is negative, T2 to T2 dash, this negative current, and this negative current we have shown with a red color, and this current will be flowing through the diode as the switch is on. Okay, current will flow through the but current, this switch is particularly unidirectional, so the red current will flow through the diode up to the T2 dash, and once the current becomes positive, we can say that our switch will carry the current. Though switch is on at T2, Though the switch is on at T2, it will not carry the current. It will carry the current after T2 dash, and that carry current we have shown with a blue color. Okay, we have shown with. So this is our equivalent circuit. So we have turned switch is made on at T2 when voltage across the capacitor becomes 0. At instant we turn on the switch. So turn on of the switch is at 0 voltage. But during that at T2 we have seen that our current is negative, and that negative current will be flowing through the diode, and voltage across the switch is 0.7 volt, and we turn on the switch. So turn on of the switch is at 0 voltage. And once our current becomes positive, the switch will carry the current. So this is the instant we have shown it here, a T0, where we are turn off the switch at 0 voltage. Similarly at T2 we turn on the switch at 0 voltage. So both turn on and turn off will be at 0 voltage. Now if you look at here, okay, the same graph we are shown it here. If you see it here, what is the voltage across the VC? Okay, voltage across the VC when the switch is off, and this voltage across VC may be almost going to a 2 times of the VD. Okay, 2 times of the VD. So that will be a voltage across the switch. So here, though we are turning on and turning off at 0 voltage, but the voltage across switch will be appearing to a higher value. Voltage across the switch will be a higher value. And here we have shown this particular period. Okay, so we are calling at, this is a diode, we are having a freewheeling diode, you can call it here, and the voltage across it will be VOR. When the switch is on, very simple logic, when the switch is on, diode is off. And so particularly when the switch is off, when the switch is on, that is here T3 to T4 period, our switch is on, and when the switch is on, our diode will be off. When the switch is on, diode will be off. Only that voltage across the diode will present, and that magnitude of voltage will be, we are having almost the VD. So T3 to T4 period, where our T3 to T4 period, if you see here, in that case our switch is on, and as the switch is on, our diode is off, and as diode is off, our whatever VD voltage will be appearing across the output. So during T3 to T4 period, our diode is off, VOI is off, and during that period our output voltage across VOI, that is diode, and that across the diode we have shown it here, T3 to T4 period. So this is the off period we are having, and this is the on period of the, this is the on period of the switch, T3 to T4. T3 to T4 is the on period of the switch, whereas T1 to T3 or T0 to T3 you can call as off period of the switch. And now which will be a constant depending upon L and C? So here we have shown the 2 periods. Is it right? Let us know T1, T0 to T3. That will be off period of the switch. And T3 to T4, that will be on period of the switch. The T3 to T4 on period of the switch we have shown. Out of that, which period depends upon LR and CR? Hello, am I audible?
Yes, sir.
So my question is, we have shown it here, at T0, we turn off the switch, and switch will remain off till T2, or you can call it as a till T3, let us assume that. Our switch is off from T0 to T3, and switch will on from T3 to T4. Out of that, which period? Is it an on period or off period? That depends upon the LR and CR.
Off period.
Okay, turn off period will depend upon this, and on period will be we can control it. Means here, if you increase frequency, which period will decrease? If you increase frequency, which period will decrease? Our off period is fixed. If you increase frequency, T period will decrease, and as our T off period is fixed, our on period will decrease. Is it right? As frequency increases, our on period will decrease. So what will happen as our frequency increases? What will happen to the output voltage? In case of
Decrease.
output voltage, as frequency increases, output voltage will
Decrease.
decrease. Output voltage will decrease as frequency increases, because as frequency increases, this off period is fixed. Our on period will be goes on decreasing, and that's why duty ratio will goes on decreasing. So as frequency increases, output voltage will goes on decreasing. That is, reverse is happening in case of uh, ZVS. Whereas in case of ZCS, as frequency increases, our off period decreases, so output voltage will increase. That is, the reverse is happening in case of ZCS and ZVS. In case of ZVS, zero voltage switching, as frequency increases, output voltage decreases. In case of ZCS, as frequency increases, output voltage increases. So that is the difference what we are having. So is it clear? What is the difference? What will happen in case of ZVS with frequency output voltage? What will happen in case of ZCS with with switching frequency?
Yes, sir.
Is it clear?
Yes, sir.
Once again, I will repeat. In case of ZCS, zero current switching, our output voltage increases with increase in frequency. Whereas in case of ZVS, output voltage decreases with increase in the switching frequency. So we have to use which method we have to use for controlling the output voltage. In both cases, we are using the frequency control to control the output voltage. Now here comparison. So we have seen that ZCS has to carry the peak current, whereas ZVS has to withstand the forward voltage greater than the input voltage. We have seen the voltage across VC in case of ZVS. In case of ZVS, we have seen that the VC voltage will be higher. VD is the input voltage, but definitely voltage appearing across the switch is maybe more than 2 to 3 times of the input voltage. So that is the difference here. So ZVS has to withstand higher forward voltage than the input voltage, whereas zero current switching has to carry a peak current than that of the load current. And so here, here we are having, for proper operation of this ZCS and ZVS, here I0 is the output current of the circuit, and output current that will be given by VD by Z0. That value, VD is the input voltage, Z0 is the characteristics impedance depending upon L and C, and based on that, so our output current in case of ZCS, output current should be less than VD by Z0. Output current of the circuit should be less than VD by Z0 for a proper operation of zero current switching, proper operation of zero current switching, where Z is the characteristics impedance. What is the value of Z0 characteristic impedance? Square root of, what is the characteristics impedance of LC circuit? What will be characteristics impedance of LC circuit? Square root of
L by C.
LR by CR. Okay. So here Z0 value is the square root of LR by CR. We find out what are values of LR and CR used. From that you find out Z0. You are knowing the input voltage. We find out the VD by Z0, that value of current. And in case of ZCS, our whatever output current should be less than this. Whereas in case of ZVS, we find out this VD by Z0 and our output current should be greater than VD by Z0. Okay. So this is the proper operation. What should be load on the this circuit, whatever ZCS and ZVS will depend upon the load on the circuit. So, and we have to take care that our load should be whatever these two conditions, our load requirement should be satisfied these two conditions for proper operation as a zero current switching or the zero voltage switching. Okay. And now here we are showing the zero voltage switching is preferred over the zero current switching. So we have discussed both zero voltage as well as zero current. But if you compare these two, so we are having a zero voltage switching is preferred over the zero current, and the reason lies in the junction capacitances. So here we have shown the, let us assume that we are having a MOSFET or IGBT, and we are having a 3 junction capacitances. What are these 3 junction capacitances? Capacitance between drain and source, that is a CDS. Capacitance between drain and gate, capacitor between gate and source. And now if you are having a zero current switching, in that case when the current is zero in the switch, but definitely voltage across the switch will be present, and because of voltage across the switch, we have seen that this CDS will be a charging. Internal capacitance will have a definite charge across it, and when the switch closes, this charge will be flowing through the switch, and because of that definitely this charge on the capacitor, junction capacitor, will lead to a switching losses in case of zero current switching. But whenever we are having a zero voltage switching, in that case the voltage across that junction capacitance is zero, and so there will not be a loss. So here we are discussing why ZVS is preferred compared to the ZCS. And here we say when the switch is turned on at zero current, turning on at zero current, but finite voltage will be across the switch, and because of that voltage, our internal capacitance will have a charge, and they will discharge to the device, resulting in the switching loss in the device. So though we are preferring the zero current switching, there will be a loss because of the discharging of these capacitors to the device, junction capacitance to the device. But when the device turns on at zero voltage, then there will not be charge across the capacitor, junction capacitance, and so that this loss will be absent. And that is the reason why we prefer the ZVS compared to a ZCS. But if you want to have a ZVS, what is problem? Device required should have a higher voltage. Device should have a device has to withstand the higher forward voltage, or voltage across the switch should appear as the more voltage will appear across the switch. So any question? Is it right? We discussed the two zero voltage switching and zero current switching, and this we can apply for a DC to DC buck converter. So any question?
No, sir.
So at least is it clear? ZCS, our device current rating should be high in case of zero current switching, and device voltage rating should be high in case of zero voltage switching. Okay, that will be the major difference between that. ZCS, we have seen that our on period is fixed in case of ZCS, whereas in case of ZVS, off period is fixed. So one case, in case of ZCS, output voltage increases with frequency, whereas in case of ZVS, output voltage decreases with increase in a frequency. So this will be the differences between this and what is essential requirement for load current in case of ZCS and in case of a ZVS. So now our interest is we want to go for a third topology of resonant switch. We have seen a ZVS, we seen a ZCS, zero current switching, zero voltage switching, and now we are going for third, that is a zero voltage switching, clamped voltage. So we are having a third topology in the resonant switch, a third topology in the resonant switch, and that is we can call as ZVS, zero voltage switching, clamped voltage. CV means clamped voltage. So in case of conventional ZVS, zero voltage switching, conventional zero voltage switching, we have seen that we obtain a zero voltage switching, but the device voltage appearing will be a more across the switch. And to eliminate this problem, we are going for a zero voltage switching, and we are clamping the voltage equal to a DC voltage. So here a ZVS CV, that is a third topology, we are going for this, and again we are applying this topology to a DC to DC converter. Now here we have shown it here. This will be a DC to DC converter, or also you can call as a DC to AC, particularly you can call also as the once you go for, okay, so this is okay, let us stick to a DC to DC converter. Again here if you see it here, VD is our input voltage. Here we are having the two devices, okay, complementary pair, so T plus and T minus. Similarly diodes we are using, okay, two quadrant converter, and these capacitors we are using. So what is purpose of capacitor? Purpose of capacitor is for a zero voltage switching. We can use the capacitors, okay, and also we are using the diodes for clamping the voltage to the DC voltage level. So here this particularly it is a DC to DC converter. Our input voltage is VD. It consisting of two fully controlled switches. We can mark as T plus, T minus, diodes, and then we are having the two capacitors and filter capacitance LF and CF, and this is I0 and this is the load resistance. Okay, and now this we can hear particularly this CF. Okay, we are having a large value of capacitance, let us assume here, and so that the CF and this VO that will be represented as a voltage. Okay, let us assume that this will be capacitor CF is a large value, LF is less here, and CF is large, so we represented this load as a VO, voltage source. Output we represented here, load we represented as the VO. This so CF and VO, CF and the load we represented as a voltage source VO. This is the LF we are having, and we are having these components. And here what we are assumption here, now our CF is very large. Okay, CF is very large, and here LF we are assuming that here LF is reversing its polarity. LF current to the LF will be reverse, positive current as well as the negative current. Okay, so that is under that assumption we are analyzing this circuit. So here we are assuming under certain conditions that this IL current through the LF, it will be a very short duration, it will also the reverse. Okay, so this topology we have to discuss. Now here, so let us consider this is a first waveform. This waveform is voltage across the capacitor C minus. This waveform is a particularly voltage across the C minus, or you can call it will be across the here C minus. So this is the one waveform we have drawn that will be VOI, that is the voltage across the C minus capacitors. And another quantity that we are represented is the IL, a current through the particularly the inductors, and we assume that our inductor value is less. And so here we have shown the current may go to a negative value. Okay, current may go to a negative value. So this is our IL. So IL is nothing but the current through the filter inductance. Inductance value is less, that is our assumption, and with that our IL current will have some duration. Let us assume that T0 to T2. Okay, here our current will become a negative here. Now how we achieve, okay, how we achieve the zero voltage switching and clamping of the voltage across each device. We have seen that voltage is clamped to a input voltage. So when a particular switch is on, the voltage will not go to a higher value because of the diode, and so voltage will be a clamp to a input voltage. That is, if you see it here, whatever the VOI, okay, that is the voltage across this capacitor, is nothing but the voltage across one of the switch. And this voltage is always, we are having maximum voltage will be equal to a supply voltage. So voltage across the switch will be remain fixed, particularly for this case. And now we have shown it here, the current and the, what will be a conduction here. What is the voltage at VO, particularly this, and current based on that which device it will be conducting. So device conduction depends upon what is the voltage available, okay, and the current through this. Let us consider here, let us take a plain case here. D minus is on. Okay, when the D minus is on, so when the D minus is on, it means that our voltage across the capacitor is 0, and particularly current is a positive. So I'll just try to show it here. Let us consider this period. This is a period I am showing with red color. In that case, what is happening here? Voltage across this capacitor is 0. Means we require a 0 voltage, but our current is positive. Current is positive means this will be a current positive. Who will supply this positive current? Definitely the diode D minus will give this. So here, if you see it here, whenever voltage is 0 and current is positive, D minus will conduct. Voltage is 0, and current is positive, D minus will conduct. Similarly here, what will happen if the voltage is 0 but current is negative? So let us assume that voltage is 0 but current is negative. Now current will be flowing like this. So this. So 0 voltage means this point we have to short this. So here, when the voltage is 0 but the current is negative, a T minus will conduct. Similarly, here if you see it, a voltage is positive but current is negative. So negative current will be this, and voltage is positive, so D plus will conduct. So D plus will conduct this. And when we require a voltage is positive and current is positive, so voltage is positive voltage is positive and current is positive, so this will be a T plus will conduct. Okay, so for positive current, either T plus or D minus will conduct. Similarly, the negative current, D plus or T minus will conduct. And depending upon the voltage, we have shown which device will be conducting. And we have seen that how we are getting a zero voltage switching, how we are obtaining the zero voltage switching. So first D minus is conducting, then our T minus we are turned on. When D minus is conducting, it means the voltage across it will be zero. So first D minus is conducting, then we turn on T minus. So device will be T minus will be turned on at a zero. You can call it as a zero voltage. Whereas the turn off, when we turning it off, when device is on, voltage across the capacitor is zero, and when you turns it off, so turn off will be at a zero voltage. So turn off will be at zero voltage because of the voltage across the capacitor will be a zero. That is why turn off at zero voltage. Turn on at zero voltage because anti-parallel diode is conducting prior to the turn on. So here if you see it here, so D plus is conducting before T plus, so that our device T plus we turn on at zero voltage. When you turn off, we add that our voltage capacitor will be across the switch and which is having a zero voltage, so the turn off will be at zero. So this is how it happens, how we obtain the zero voltage and the how we obtain the zero voltage turn on and turn off, and we can always clamp the voltage equal to a VD. So that is the benefit. So in summary, we are having three topologies of the resonance switch. So first is we are having a ZCS. We are discussed for all these three cases. We are discussed for a buck converter. Is it right? All the three cases we have discussed for the buck converter, DC to DC buck converter. This is what we are having LR and CR configuration, and we have seen that we can get the zero current turn on and the turn off. But here, what is the drawback? We require a large current. Switch has to carry the large current. Switch has to carry the large current in case of ZCS. In case of ZVS, the voltage appearing across the switch may be 2 times of the VD because of the capacitor, resonating capacitor voltage across may reach to a 2 times of the VD, and that's why the voltage rating of the switch required will be higher. And the third configuration where we can have a zero voltage switching, at the same time our voltage across switch is limited to equal to a input voltage, and that topology we can call as ZVS clamped voltage, zero voltage switching, a clamped voltage. In that case, particularly we require two devices. Okay, not it is not possible with a single device. We require this type of the circuit configuration for ZVS CV. So this will our complete resonant switch converters. Earlier we discussed the resonant load converters, and third remaining is the resonant link converter, DC link converter, so that we can go for next. So any questions on this ZCS, ZVS and ZVS CV? So out of that, which will be a preferred one? ZCS, ZVS and ZVS CV. So which topology is better out of these three?
ZVS CV.
ZVS CV is better because our turn on and turn off at zero voltage. At the same time, there is no voltage trace across the device. Voltage rating required will be corresponding to a VD. So we can say that ZVS CV will be the better option, but we require one additional device for that. Is it right? We require the additional device, one additional device. All these two topologies are with one device, but here we require this topology with the two devices. So that will be a comparison between these three. So any question? one announcement is there. You have to complete our 6 experiments. What should be a submission date we can give for this?
Next week, sir.
Next week, is it 12th? So we'll make a one Google form and you upload your files on that experiment number 1 to as per roll number. Whatever we are taking a assignment, you are uploading the answers. Similarly, you upload your practicals 1 to 6. Okay, I will make this Google assignment form, okay, where you can put up your experiments. So what date we can confirm? Before that you have to do this. Can it be a 12th of October when your LA2 is there or T2 is there?
18th of October.
18th. Before that we have to do. Is it right? 12th or 13th, which will be a convenient?
13th.
Okay, so 13, before 13 delivery, that particularly Google form will be available maybe within 2 days. Okay, when you complete, you can finish and submit. So all 6 experiments should be those who are not completed, all the 6 are incomplete. There are so many possibilities. Okay, one is same experiment may be placed 3 times. He has written 2 experiments and one experiment is putting at 3 times. If this activities happen, if this is found, okay, he will straightway he will get for your second assignment, second evaluation 0 marks. Okay, so you don't cheat, first thing. So all 6 experiments should be ready. And if you are mischievous, if anybody is doing like this, definitely he will be penalized. Okay, we'll give us straightway 0 marks to your second lab assessment. So that is very, very important. So whatever 6 experiment, you take care. Okay, say that I have hurriedly uploaded or whatever it may be. We don't want to listen any reason for this. Whatever all 6 experiments, you should be upload. You don't upload the friends experiment PDF file. We are observing at a one time, and there should not be change in the handwriting. Okay, that you should also take care. Okay, that you should be written. You don't use the friends observation table and make the PDF and submit. That should not happen. Okay, so you should take care that you do your work, and our last date for submission of these 6 experiments will be 13th of October. Is it okay?
Okay, sir.
Okay, okay, we'll be tomorrow at the same time, 10:50 a.m. Thank you.